Let me just, for the recording, say happy birthday, Oscar. Thank you for organizing a nice conference, for coming with a good date for the conference. Okay, so I'd like to say, just to start with just a few comments about some of Oscar's very numerous and great papers concerning parabolic bundles, which is, of course, it's a small piece. I think Steve had a nice segment of the map, and you can notice that for a while the little thing up in the corner was kind of lonely, although it got filled in a little bit later. But I think this is an interesting point. Okay, so one of the first calculations of Betty numbers of moduli spaces after Nigel's original work was the case of rank 3 parabolic Higgs bundle. That was a pretty major thing. Of course, now we know a lot more about that. But at the time, that was quite a major accomplishment. Okay, then another very interesting paper is on moduli spaces of parabolic UPQ Higgs bundles. And here again, I think it's also will be interesting to look more at this paper in terms of what happens in the case of special position monodromy transformations. But this is a very general paper giving the general structure of the theory of parabolic and parahoric bundles for principal G bundle for real groups. And so some of the calculations which we're about to do, well, I should also say we also saw them in the previous talk a little bit, but also they're done in this paper. Then a couple other papers, actions of the mapping class group is really important. And the paper on the parabolic vortex equations. So I looked this up, and there don't seem to be very many recent people who have worked on this topic, which I think is unfortunate. And so I think this is like a very ripe topic for if anybody's looking for a subject. I would say read this paper and continue in that direction because this is clearly a fascinating idea. Okay, so now I'd like to just start by introduction to parabolic structures. So we'll be working on a curve, a compact curve X, and a divisor D, which is just a single point of X for simplicity. And there's several different ways of defining what it means to have a parabolic structure. Here's maybe the most classical way, but it's also quite useful, is the following: is to start with the definition of a quasi-parabolic structure. So a quasi-parabolic structure is just a filtration of the fiber EX at the point X. Then a parabolic structure consists of giving a quasi-parabolic structure, and then a choice of parabolic weights. And as we saw in the previous talk, those are usually stated to be inside an interval of length 1, and you can sort of choose which interval you want. So maybe for here, the normalization will be that this interval is the interval from -1 to 0, and it includes 0, but doesn't include -1. -1 is sort of the elementary transformation of the 0. Then we'll think of the weight AI as corresponding to the, sorry, this should be a mod. There's going to be some mistakes in these slides, I'm sorry. This is the mod Fi mod X minus I minus 1. Anyway, that's the associated gradient piece of the filtration. So the weights are associated not to really the filtration levels themselves, but they're really associated to these subset signs. The jumps in the filtrations. Okay, and then as I think almost everybody here probably knows very well, but let me just say this anyway. The parabolic structures are related to metrics on the bundle in the following way. So suppose we're given a Hermitian metric on the bundle, and suppose that for any section of the bundle such that which has a non-trivial reduction at the point X, then we suppose that the norm is bounded by the absolute value of Z below, and sorry about this sign, and the absolute value of Z to the minus epsilon, so just something slightly bigger than 0 above. Okay. Then we'll say that the metric is adapted to the parabolic structure if for any element which is in for any element set for any section E such that the reduction at the point X is inside the ith level of filtration, but not the I-1 level of filtration, then the norm of E should behave approximately like absolute value of Z to the minus AI. Let's remember that these AIs are themselves negative numbers, so these are positive. things. And so we get to the case where -1, that's sections that have a behavior of the form Z, absolute value of Z. So the sections of Fi that are not in Fi -1 are sections whose growth is approximately absolute value of Z to the A, to the minus AI. Okay, and so now if the metric, of course, the general metric is not going to be related to a parabolic structure in this way, but for sufficiently nice metrics, and this includes harmonic metrics on tame Higgs bundles, then there's going to be a unique parabolic structure which reflects the growth rate of the metric. And so this can be defined by looking at the subsheaf of sections with growth less than Z to the minus A with an epsilon. And these are going to restrict to the desired filtration. This gives a subsheaf of EA, which contains the ones that vanish at 0, and then at X, and then the image of that into the fiber or the filtration level. So let's see now. We'll just recall about tame parabolic Higgs bundles. The tame parabolic Higgs bundle is a pair E5, where phi is an endomorphism of E with coefficients in Kx with poles at the divisor D. We're assuming that the divisor is reduced. And we can write this as E tensor omega 1x of log D, and a parabolic structure such that the residue of the Higgs field, which is a well-defined endomorphism of the fiber, right? The residue is a map from omega 1x of log D to the fiber at X to the complex number. And we regard that the residue respects the filtration. Then it's called a strictly parabolic bundle if the residue descends the filtration by 1 step. Then we'll define the associated graded space to be the sum of the graded pieces of the filtration. And the graded residue is then the action of the residue of phi on this associated graded piece, because the residue of phi preserves the filtration, so it induces an endomorphism of each of these pieces. Then the strictly parabolic condition says that the residue is 0, the graded residue is 0. I'm going to just denote the graded residue by res, because that's the main object of interest here. The strictly parabolic condition is the condition that this residue sends Fi into F minus 1, I minus 1, which means that it's trivial on the quotient. So the graded residue might not be the same as the full residue. So if you have, for example, a strictly parabolic Higgs bundle, then it could have a nilpotent part, which is the part which descends to filtration. And we don't really have too much control over that, except that part of the residue really doesn't get reflected in the connection that's corresponding to the Higgs bundle. So it's this graded residue that we'll call res phi, which reflects the monodromy of the associated flat connection. And here again, there's also you need to say something more precise here, which is there's going to be a type of parabolic structure on the flat connection, and the thing which corresponds to the residue of the Higgs field is the residue of the monodrome. Now I'd like to do some calculations in the rank 1 case to illustrate the thing I'm trying to say. This is from a long time ago. But also I think it's a good exercise if people are interested in getting into the subject. This is a good exercise. So let's do the calculations in the unitary gauge. You could also do them in the holomorphic gauge in terms of Hermitian metrics. Let's take Nigel's original notation in his original paper, in fact, and use a unitary gauge. So we'll fix a C infinity line bundle with a constant unitary metric. We'll consider a connection, dA, which is, and then we're going to be taking model connections here. In fact, we actually saw these in the previous talk. We're going to be taking model connections which are logarithmic in nature and rotationally invariant. It turns out that those will be the model metrics that model the general behavior. The model connection. Okay, so a unitary connection, if I'm not mistaken here, I maybe made a mistake when I was writing this up, but I think this is correct now. A unitary connection is going to be written as D plus some real constant times dz bar over z bar minus dz over z. And this is involved, this already involves a certain amount of gauge fixing. So we're fixing that the radial part of the connection is trivial. And why can you do that? Because if you had a non-trivial radial part of the connection, then you could just make a change of gauge that depends on the radial part of the polar coordinates. You'd sort of be twisting the bundle as you move into the origin. So when we write something like this, we're already making a gauge fixing thing. But this gauge fixing exists. I mean, the gauge transformation exists to stand up to this case. So we kind of see that. Now we consider a Higgs field. So that's going to be again with this logarithmic form. So it's just going to be a number times dz over z. And this is holomorphic, and the connection is flat. And you can check that this connection is flat. And so these give solutions of Hitchin's equation. We'll note that the phi adjoint plus phi adjoint phi term is actually 0 here because it's a commutator. If you write what that means in terms of matrices, that's a commutator. This is a plus, but it's a 1 form, so that's why it's a commutator. And we're in rank 1. So that term doesn't add anything to the curvature. So the Hitchin equation split into 2 pieces there. And so in fact, the equation for having Higgs bundle in the rank 1 case is just to have a holomorphic Higgs bundle. And so then we can write the resulting flat connection like that. Sorry. I forgot the D part here. Sorry. The D here. As I said, I'm sorry about the slides, which are a little bit containing mistakes. Now from this connection, but okay, let's remember we had the del plus del bar part, the trivial del plus del bar part here had to be missing, had to be included. This has a 0, 1 component, which is a over 2 dz bar over z bar plus p bar dz bar over z bar. And so that's going to be a general d-bar operator, as we saw in the previous talking back. In the general d-bar of the operator of the form del bar, the constant del bar plus some number times dz bar over z bar. And so you'd like to know, we'd like to be able to solve the d-bar equation and get some holomorphic section. And we'd like a holomorphic section which is well defined as we go around the board. So you can see that to get a solution of the equation, you have to take z bar to the power minus q. Again, if I'm not mistaken about the sign there. You have to take z bar to the minus q, but you want something that's single valued. So to get something single valued, if you pair the z bar with a z, then this becomes a real number. And so remember, q is a complex number, but a real number to the power of a complex number, that's actually a well-defined thing. If we didn't put the z inside here, you'd have this complex number to the power of some other complex number. There's no guarantee onto what happens when you go around the origin in that case. So the way to get a single valued solution of the d-bar equation is to take z bar to the power minus q. We'll note that the growth rate of this section is absolute value of z to the minus 2 real part of q. 2 because there's the z and the bar. Okay, so now if we go back, so let's just go back here. If we just take this section, this connection without the Higgs field, okay, the z bar part is a over 2 times d bar over z bar. So if we use d bar q as the 0, 1 part of this just a, then q is equal to a over 2, and our frame is z bar to the minus a over 2, and the growth rate is absolute value of z to the minus a, which means that with our notations, that means that the parabolic weight of the bundle is a. That was why the a over 2 normalization came in there. Now, sorry. Right. Why are we doing this? Because I know. Oh, okay. Well, here we're going to the general connection. So the monodromy of this connection. I'm sorry. Yeah. Okay. Sorry. Why am I using this? Because the holomorphic bundle of the Higgs bundle is just. It's not including this part, right? That's the part of the flat connection when it comes from the Higgs field. So we'll be including that in a minute. But the holomorphic part of the Higgs bundle itself is just the a over 2 dz bar over z bar, right? So the parabolic weight of the Higgs bundle is a. And then the monodromy, well, the monodromy up to a question of which orientation you take. But the monodromy is the exponential of the path integral around the loop of the whole connection, basically, all the connection form. And remember that the integral of d bar over z bar is going to be minus the integral of d over z. And I think that should be 2 pi I. So altogether, you get 2 pi I times p minus a minus p bar, which is 2 pi times the imaginary part of p minus 2 pi times a. Okay. So we can see that the monomer is the exponential of that. So there's a rotational part, which is the e to the 2 pi I a. That I think we all know that that should exist in the case of a parabolic weight a. And then there's a real part, which is a real scalar part, e to the 2 pi times the imaginary part of p. So what we see here is that if we have, let's go back here. We start with the Higgs bundle that has this level A parabolic structure and has a residue of the form p dz over z. We're going to get something where we see the parabolic structure as the rotational part of the monodromy. And we see the imaginary part of the Higgs field as the imaginary part of the residue of the Higgs field as the real scalar part of the monodromy. So then without doing this calculation, you can calculate the real part of P. We've accounted for the imaginary part of P, but what about the real part of P? The real part of P determines the growth rate of a flat section of the full connection along an array where you go to the origin. And you can formalize this in having the notion of filtered local system, which is to say a local system provided with something which is analogous to a parabolic structure, which determines the polynomial growth rates of norms of flat sections. The only difference being that the parabolic weights in that case are any real numbers because you don't have the elementary transformation that multiplying by z. There's no modifications of the bundle in the case of a local system. So the growth rate of a flat section could be absolute value z to any real power. So now let's so that we treated the Higgs bundle case and the monodromy case. What about the more general case of lambda connection? So we can recall that when you have a Higgs bundle and when you have a solution of Hitchin's equation, we create an operator d prime, which is the del A plus phi adjoint. We create an operator d double prime, which contains the Higgs information, del bar A plus phi. And we set d lambda to be lambda times d prime plus d double prime. So that's should be this formula. Yeah. And so, but now let's take this connection. This is a connection. This is a lambda connection. So it's a connection that has a d bar part and a lambda times the del part. Okay. But so we can extract the d bar part of that connection, the 0,1 part of this connection. So a little lost here. Let's just recall it. The main case we're interested in is the case lambda equals 1, where we're talking about a holomorphic bundle with connection. It's just sort of going to be interesting, as we'll see in a minute, to keep the lambda in the formula. Okay, but this thing now has a holomorphic frame of the form, as we saw before, z bar to the minus q, where q is a over 2 plus lambda times p bar, right? Because that's the coefficient of the d bar over z bar part. That has so that holomorphic frame has a growth rate of z to the minus b lambda, where the parabolic weight parameter now is b lambda equals a plus 2 times the real part of lambda times p bar. We can't say lambda times the real part of p bar because lambda might itself be complex. So this is a sort of non-trivial operation, combining the real and imaginary parts. And so we would also like to figure out what's the residue of logarithmic lambda connection on the holomorphic bundle. So it means we need to solve the equation. Okay. So we remember our solution was this f, which is z bar to the minus q. Then we can take the 1,0 part of the lambda connection applied to f, and we get something like this. So the point is that the q enters into the formula because it's the derivative of the z to the q. It's minus lambda times q because it's lambda times the derivative. So we have a holomorphic bundle that has a logarithmic lambda connection, and the residue of logarithmic lambda connection is p minus lambda a minus lambda squared p bar. And so if lambda equals 0, this is the Higgs case. So the residue is p. That's the way we set it up, and the parabolic weight is a. at lambda equals 1, the parabolic weight, sorry, I have to back up here. Parabolic weight at lambda equals 1 is just A plus 2 times the real part of P. So the parabolic weight is A plus 2 times the real part of P, and the residue is 2I times the imaginary part of P minus A. So that's the vector bundle with holomorphic logarithmic connection that's associated. Then one can show that these calculations on toy examples actually are the correct local models for the rank 1 pieces of tame solutions of Hitchens equation. And so getting a statement relating the strings and the unipotent parts of the monotomy or the nilpotent parts of the residues, which form strings in the Jordan normal forms, those actually do also relate among all the different sides. Showing that is more complicated. But it doesn't really modify the metric too much because it modifies the metric by R's norm of Z, by log R to some power. So it doesn't change the growth rates that are polynomial in R. So if we're only interested in questions about parabolic structures in terms of polynomial growth rates, we can sort of ignore that part. So the summary, to sum up, we have a solution of Hitchens equations yields a logarithmic lambda connection that has the form D plus, that should be D lambda, sorry. D lambda plus B lambda dz over Z. Yeah, that's a lambda, I'm sorry. And the metric should be given by the metric size of the frame section is Z to the minus D lambda. The parabolic weight is A plus 2 real part of bar, and B lambda is P minus A lambda A minus lambda squared. Okay, so here we get these equations. You can actually see these in Saba and Mochizuki's books. They were the first ones to consider the general lambda case. In the case lambda equals 0, lambda equals 1, those I had those in a table in one of my papers. And we should note that these are well defined up to an operation of gauge transformation, where we change the parabolic weight by an integer, and that changes the residue by lambda times that integer. Okay? That sort of plays an important role in the general theory. That corresponds to different choices of extension of the holomorphic line model across the origin. Okay, so let's make a couple of observations. So we can make a few general observations. In the rank 1, in a rank 1 piece of the picture, the local structure is governed by 3 real parameters, not 2. These parameters group into a complex parameter and a real parameter. And the splitting into the different parameters is different between the Higgs field, the monotomy, or lambda connections, and so on. And so the question is what's going on and how do we explain this? And so the claim I would like to make here is that this sort of strange looking collection of transformations, it's actually a manifestation of the quaternionic structure on the moduli space of Higgs bundle that Nigel introduced in his paper, but in a way that corresponds to Hodge weight 2 rather than Hodge weight 1. So the quaternionics, we'll see in a minute, the quaternionic structure corresponds to Hodge weight 1. And this slightly bizarre collection of transformations like that's basically corresponding to weight 2. That's the idea. Okay, so now let's go back and review the Twistor theory. So this is probably in your paper with Carly and so on, right? But I guess it comes from before. I don't know what what's the original origin of this, but anyway, goes back quite some time, but I'm not sure it goes back to the first beginnings of the quaternions themselves, but almost. Okay, so let's take the algebra of quaternions. Well, this part definitely should. So you have a space of complex structures inside the quaternion. So all the quaternions that themselves satisfy k squared, kappa squared equals -1, that's given by a sphere, actually. So we have a 2-sphere S2 of complex structures. And by some formulas that you have a complex structure on that thing, and that becomes P1. Okay. So then we can view P1 as a set of complex structures given inside the algebra of quaternions. And now the complex structure I, for example, of course, depends on your normalization. I might be making a mistake here, but I think I corresponds to 0 in P1 and J corresponds to 1. Okay, now suppose we have a quaternionic vector space, in other words, an H module. Then for each complex structure element, we get a complex structure. And so we get a C vector space, okay? And now you can make what's called the Twistor space by taking the product V cross P1 and declaring that the complex structure declaring that the P1 has its complex structure and declaring that the complex structure for any value kappa inside P1, the complex structure on V is the one given by V kappa. You get the total space of a vector bundle, which we'll call cal. Then we call sections of V that have the form some vector cross P1. We'll call those preferred sections. Then there's the antipodal involution of the sphere, x, y, z goes to minus x minus y minus z. That corresponds to the thing you get. It's easy to remember this. You just product together all the different involutions you can think of on P1. Okay. once you're done, you can't think of any other ones, then that's it. Minus lambda bar inverse. Okay, so this involution is a real structure on P1, except which has an empty set of real points, but it's interesting to think of that as a real structure. And now the vector bundle V is going to be provided with an involution defined by just applying the involution to the second coordinate. This is antilinear and covers sigma on the base. Okay. And then it turns out that the preferred sections are the only homomorphic sections that are compatible with this involution. No, they're fixed by the involution. So suppose we just take H itself, then V turns out to be OP of 1 direct sum 2 times, right? So remember, each fiber is a complex vector space that is the quaternionic vector space provided with that complex structure. So whatever the dimension of the quaternionic vector space is, the dimension of the complex vector space is twice that. So we take a one-dimensional quaternionic vector space, we'll get a rank 2 bundle. And any H module, any H vector space is just a direct sum. So this gives a structure for this linear. Then you can prove a converse of this, which is that suppose you have a vector bundle with a involution compatible with the, I should say antilinear, involution compatible with the, I guess anti-homomorphic, compatible with the structure on sigma. And suppose that V is semi-stable of slope 1. That's to say, suppose V is a direct sum of O of P1 of 1. Then it comes from a quaternionic vector space. And you can get the quaternionic structure but in the following way, that for any point in P1, the projection from this vector space to the set of values on K, at kappa, is an isomorphism of real vector spaces that induces that complex structure on V. You can get I, J, and K by just restricting to 0, 1, and I. What's the basic idea of why this is true? Well, if you have a semi-stable vector bundle of slope 1, then given any 2 points, the evaluation map is an isomorphism. Just as the a section of O of 1 you can is determined uniquely by its values at 2 points. Okay, so gamma, the space of sections of V is going to be isomorphic to Vx plus Vy. And suppose we choose the points kappa and sigma kappa. Okay, then there's going to be a section given any 2 values, but if we take those values to be sigma related, then that's going to be a sigma invariant section by the uniqueness. So there's going to be a unique sigma invariant section with a given value at a single point. This gives us our isomorphism. So kappa determines a complex structure on this fixed vector space. And this is the way you can see the family of complex structures. So now you can do the same thing. I should probably go a little faster. Significantly faster. When should I stop?
I should stop in 21 minutes.
Okay.
You said
that should be fine. Okay.
Yeah.
Okay. I'll try to
21.
Anyway, so we can still go faster. So we can do the same thing for a quaternionic manifold. We can again define the Twistor space to just be M cross P1. The horizontal preferred sections are just the ones given by a point cross P1. And on each fiber, the complex structure of the fiber is given by that complex structure acting on the tangent spaces of M. Then you need to say something here to say you've got an integrable complex structure. And so you've got a complex structure on the But then now, Hitchin defines a quaternion structure on the moduli space of local system and considers the true space. Then furthermore, it actually has a metric, so it has a Riemann metric that's scalar for each complex structure. And then the Twistor space is sort of a central object in studying this non-unit Hodge correspondence. Okay, if kappa equals I, which corresponds to lambda equals 0, then the moduli space is M0, which is the moduli space of Higgs bundle. And for the complex structure corresponding to lambda equals 1, the moduli space is the moduli space of vector bundles with integrable connection. Then for lambda between 0 and 1, as we'll see in a minute, it's the space of lambda connection. These M kappa for lambda different from 0 or infinity, they're all naturally isomorphic to the moduli space of local system or representations. I mean, they're all isomorphic to M1, and then in turn by the Riemann-Hilbert correspondence. Those are isomorphic to the moduli to the character body. Then Dewey actually says he said Witten was explaining the Hitchin's construction and then explained that's supposed to work. So maybe we should say Witten Dewey or something like that. Anyway, so Dewey sent me a letter where he explained it. So he gave an interpretation of this construction, which I think is basically, I think it's basically in your paper, roughly speaking. But
yeah,
with a
there's an algebraic aspect to this.
Yeah, there's a Dewey type of thing going on here. Okay, so here's the way to think of this. So if we take lambda different from 0, we can just rescale back to get an actual connection. Okay, but for lambda equals 0, we have a Higgs field. So we can make a construction in algebraic geometry to construct this family of moduli spaces. So we construct a moduli functor, which is vector bundles with a lambda connection and so on. Then we can, if we do a sort of a motivic language for these objects, then we can see that this moduli space actually corresponds to the Hodge filtration on the Durand cohomology space. And so we'll denote this by M Hodge. Now the rescaling thing gives you a trivialization M Hodge over the open set lambda different from 0, isomorphic to just GM cross the Betty moduli space. This is the analytic. And then we can also make an identification between X and X bar. Topologically, they're the same space. And so the Betty moduli spaces of X and X bar are identified. Then up to some question of signs, which I confuse me still and always will, I don't think I'll ever not be confused by these things. But anyway, you can define a gluing between the Hodge moduli space for X and the Hodge moduli space for X bar. So X bar here, so let's be precise about what's X bar. So if X is an algebraic variety, it's defined by some equation. X bar is the algebraic variety defined by the same equation, but where you bar all of the coefficients of the equation. And then the map X1 xk maps to X1 bar xk bar from projective space to projective space. That gives you a anti-linear, an anti-holomorphic map between X and X bar, which is a topological identification. That's this identification. Then we can glue along that identification, right? So we missed something here. We get embedded X isomorphic embedded X bar. So then if we cross with a GM, we get an identification of these open pieces. So we can glue these two pieces together, and this gives us something which we usually call gluing Hitchin now because different interpretations. And so and this is designed so that we can also construct in a way the antithetical involution. So I guess so one point to point out here is that this space is defined using only complex analysis, namely the Riemann-Hilbert correspondence. We didn't use any sort of nonlinear or Yang-Mills type of stuff to construct this space. But it does require some analysis because we needed to use the Riemann-Hilbert correspondence that integrates a connection to its representation.
Now you are in any dimension, X is any dimension, and the non-abelian situation, right?
No, here X is a curve.
Oh, it's this, okay.
Oh, that's yeah.
Okay, and you are now in the non-abelian situation, right?
Yeah.
Okay.
Well, although, no, actually, your word.
Still in the
Yeah. Okay. We'll get to the non-abelian situation.
Yeah.
But I mean, this is just this is sorry. This is really general in the case where X is compact. You might say for general. This is kind of reviewing. I should go a little faster. And so then the theorem is that this construction gives you the same thing as the Twistor space of Nigel's quaternionic structure. In such a way that the preferred sections of the Twistor space correspond to sections of the vibration that we'll also call preferred sections that are obtained whenever we have a harmonic bundle, which we'll write in this way, corresponding to a solution of Hitchin's equations in the following way. We take the value for at a point lambda is the holomorphic bundle, which is given by the whole. This is the zero. This is we met this before. This is the d lambda 0, 1 part, right? This is the holomorphic part of the d lambda thing. And then this is the lambda connection acting on that holomorphic bundle. That gives us a point in the moduli space. That gives us a point in the algebraically defined moduli space. And these are also compatible with the antitypical involution. Then the fact that we get a quaternionic manifold, I don't think it's, I mean, you'd have to say something about polarization in order to get the hyperkilot metric. But the fact that you have a quaternionic manifold comes from this property, which is we make this definition and we define these preferred sections. Then if we take the relative tangent bundle, in other words, the tangents of the fiber over all the points of P1, pull it back by the preferred section, then we get a semi-stable vector bundle of slope 1. So this is just using the interpretation I gave at the start that says why the quaternionic structure is the same as a semi-stable bundle of slope 1 over Q. Again, then if we look at the case of Hutch structures, I mean, if the preferred section happened to come from a variation of Hutch structures, then this analogy can be maybe more precise. But just in general, as an analogy with Hutch structures, we call this property of being semi-stable of slope 1 a property of saying that it has a weight 1. So in some sense, the quaternionic structure of the character variety is a manifestation of the fact that it's some kind of degree 1 non-abelian cohomology. And so it's going to have a weight 1 Hutch structure. So this is analogous to saying that just the usual abelian cohomology, Graham cohomology, has a weight 1 Hutch structure. And you can even make a foray into étale cohomology. The étale, if I'm not mistaken, it's not my subject of expertise here, but the étale cohomology of a variety over Q bar with QL coefficients has weight 1 in the sense that the Frobenius eigenvalues have norm Q to the 1/2. So. Now, what about weight 2? What about weight 2? So let's recall that just going back to abelian cohomology, and so to get an example here, we're going to have at least 2 points, otherwise there's no local system. Okay. So let's take just P1 minus 2 points. The classical mixed Hutch structure on the abelian cohomology is one-dimensional and it has weight 2. And this corresponds in the arithmetic setting to saying that the H1, the étale cohomology of X with coefficient in QL is a tape structure called QL of 1. It's a tape twist. And if you write this down in the general case of quasi-projective curves, you can have an exact sequence with the local homology elements around the points. Those are going to be weight 2, either Hutch structures or Eletic whatever. So we can therefore conjecture that the Twistor weight 1 property should become some kind of weight 2 property for the monodromy transformations of the functions. And that's the idea. So I'll try to say this quickly for the case of rank 1, although it's running out of time here, but
So you have 11 minutes.
okay.
You have 10 minutes.
Okay.
11.
Okay. We'll see. Anyway, then the rank 2 is at the end of the notes. And but I just like to say I don't know how to do the higher rank theory yet. The idea was that the rank 2 case should give some idea about that. But that's not there now. What about the case of rank 1? So now we look instead of abelian cohomology, instead of linear abelian cohomology, we look at really abelian cohomology still, but with rank 1, with the moduli space of rank 1 local systems or Higgs bundle. Now, a logarithmic lambda connection over a trivial bundle is going to have the form, this time I put lambda in correctly, lambda d times plus a dz over z. That's really true over P1 minus 0 infinity. It's not even a toy model. Then we can write the moduli space is A1 cross C. So A1 is the lambda variable, C is the A variable, and G, what's G? We'll see that in a minute. G comes because we can make a change of trivialization, right? So the same connection can have several different logarithmic connections. The same monodramming representation can have several different logarithmic connections. And in this rank 1 case, it's kind of easy to see what they are. They're just given by adding k lambda to the residue. So this is the gauge group acting. That's going to act. I mean, you can say more generally. You could actually this is picked up so that we're keeping degree 0 bundle. So if you add something at one point, you subtract it at the other point. You could also have modify the degree of the bundle and modify the things at different points separately. So we can see that this actually acts nicely over lambda different from 0, but at lambda equals 0, it's a trivial action. So there's something not so great going on here. But now the Riemann-Hilbert corresponds for lambda different from 0 gives you, it's just the exponential sending lambda a to lambda comma exponential of 2 pi I a over lambda. That's the monodramming. Okay. So away from 0, we can take the quotient, and that quotient is just GM cross C star. Well, that's the GM cross embedding. Then we'd like to glue this to the other piece using the Deligne gluing. Let's maybe not do that. You can do the Deligne gluing and so on. Sorry. But I guess at the end, it turns out that when you do the gluing condition, you calculate that the line bundle you get is OP102. So that's, you might say, not surprising given our conjecture that it was a weight 2. And the Deligne-Hitchin moduli space is the total space of OP102 modulo whatever, however you can do this, modulo this group action, which is bad at the 2 endpoints. It also has a non-trivial, it has an antipodal involution, and we can define preferred sections and so on. So recall, we'd like to look at the space of sigma equivariant sections. And so let's look at what this is going to look like. So this is going to look like the following thing. We have OP102. We take the space of sections of OP102. That's a 3-dimensional complex vector space. And then if we take the space of sigma invariant sections, sigma is a real structure on that space, this is going to be R3. Then we can see that the restriction morphism from these sections to the fiber at any point is going to be a surjection from R3 into this complex line. Then the more difficult thing, which I'm still having trouble understanding really, is that there's a natural splitting depending on the point kappa, which splits R3 into R cross C kappa. This gives we have an exact sequence of the kernel of R, but why does that split? I think that's actually some kind of polarization information that I haven't understood anyhow. Anyway, but in any case, the splitting has the property that the generator of the gauge group is 1 comma lambda. So one way of seeing the splitting is that we can actually write this weight 2 general weight 2 structure as being the tangent bundle of P1 itself, right? The tangent bundle of P1 is O of 2, and it has an antipodal involution because it's just the tangent of the antipodal involution of P1. So that's like the basic model, and on that thing you can sort of see a little bit better the splitting. And so the idea, this is supposed to explain our question, right? So let me just go back to our question. This is supposed to explain at least the first part of our question. The local structure is governed by 3 real parameters. The parameters group into 1 complex and 1 real parameter, and the splitting is different. Okay? So that's the idea. Let's see. Let me just say. So you can do the calculations, and you can see that actually does give you the same. That gives you the same formulas that we saw in the beginning. So for the parabolic weight, we have A plus 2 times the real part of lambda P bar, and for the residue eigenvalue, you have P minus A lambda minus P bar lambda squared. these that are into Dr. Omochizuki's notion of KMS structure. So what about the higher rank case? So we have a problem with the singularity of the gauge group action here. So it's not completely clear what to do in the case of higher rank. Also, we haven't discussed stability in any way. And we can recall that the stability, the conduction of the Higgs bundle moduli space requires stability of the Higgs bundle. So we would need, in principle, in order to make a nice finite type moduli space, we would need to know something about stability, except for the fact that defining stability requires knowing something about parabolic weights, but we're trying to recover the parabolic weights from the construction. So we really need to not be talking about stability. So we're going to have moduli spaces that are not a finite type, but only locally a finite type. And we have to accept this fact. Then another problem is that, I mean, this problem of resonant eigenvalues, once you start having higher rank bundles, you have two different eigenvalues that differ by an integer, and that's going to cause some kind of singular problem. So what do we do? So the idea is to define a space of a moduli space of framed quasi-parabolic bundles with logarithmic lambda connection, and then to define a Hecke gauge group weight, which is obtained by taking Hecke transformations on the quasi-parabolic structure. And one of these transformations is only partially defined. Well, then the basic idea is that we can make a moduli stack in some way, or just some kind of groupoid, and glue those together. And let me just get the statement of there. Stop one. Is that you have a moduli space, and the tangent bundle has a filtration such that the bundle with its filtration is a mixed Twistor structure, which means that WK mod WK minus 1 is a semi-stable bundle on P1 of slope K for 0, 1, K equals 0, 1, 2. This is the weight 2 piece. This is the classical quaternionic piece, and this is the piece which corresponds to the change of framing, the frame bundles.
So the O2 and the R3 and the gauge transformations, it sounds like periodic monopoles. I mean, this is the
yeah, there's some likelihood.
Mochizuki is written a lot about that. I mean, is there some
well, probably, yeah.
an overlap there?
I guess, yeah. I think it's likely. I don't know myself exactly how, but we should maybe think of one thing, which was at the very beginning. Instead of 3 real parameters, we actually really had 4 real parameters, because if you remember at the very beginning, I said we're going to use gauge fixing to assume that you have this radial vanishing of the radial gauge thing. So maybe if you look closely at what happens if you don't try to do that gauge fixing at the start, that might at least some sort of input into that at the beginning, possibly.
This is a basic question, but you have been, I mean, the typical parabolic non-abelian Hodge correspondence requires existence theorems that are difficult and so on. And so on. Now you have been in the abelian situation, the rank one, right? So what is really involved? Can you comment on what's involved there to just prove the correspondences between all these spaces that you have?
The rank one case. I think, I mean, in my paper, which was from about more than 10 years ago, where I did this in the rank one case, I think we can pretty much do that. Let's see. So you're talking about, for example, you'd like to have a higher dimensional situation? I think that should be possible.
There is Hodge theory.
Yeah. I think that should be possible, because I think it's really the mixed Hodge theory of the. I basically have to take the mixed Hodge theory of the curve and quotient by this gauge group, and that gives you the answer. But you know, Bill Goldman and one of his co-authors wrote a book about that. About the rank one case, I think. Yeah.
Yes, yes.
Yeah.
on the parabolic.
That was, but I don't think that was the
Another
parabolic
parabolic.
case, but I think
No,
the same formula that they're using
Yeah,
there
but I'm
should probably work in the parabolic case also.
especially thinking of the parabolic case. I mean, well, what is, because in the non-parabolic case, the abelian situation is, just useful, just what you feel.
Yeah. Well, I think so. I think I just don't want to like extend myself a little bit too much here, but I think you can just write down the formulas using the mixed Hodge structure on the usual cohomology. I think that gives you the answer. I mean, there might be.
No questions? Comment? Okay, then, Charlotte again? Yes, please.